Good morning and welcome to the lecture 6.6 on applications of matrices. Um, this is a little bit complicated and we're going to go through a couple example problems to show how this is done in real life in economics, etc. And then give you some formulas. There's some key formulas in here and ways to solve problems that's a little bit different than what we've done in the past. So let's look at a simple linear system. 2x minus 3y equals 4 and x plus 5y equals 2. This is a very simple system that we know how to solve for algebraically using either substitution or elimination. We also know how to set this up as a augmented matrix and solve the system. But we're going to solve this a little bit differently, and it's important that you try this new method because you're going to need to kind of use the skills developed in this new method instead of just entering the augmented matrix and going to the reduced row epsilon form function button on your calculator. So if we let the matrix A equal what is known as the coefficient matrix, and these are the numbers in front of the variables on the left side. Notice again, all of our equations are in standard form with the variables on the left side, the constants on the right, and the variables lined up, so the x's line up, the y's, etc. So let's create a couple matrices here. The A matrix, you'll notice, is what we call the coefficient matrix. It's the constants or numbers in front of the variables on the left side. The X matrix is what we call the variable matrix, and this would eventually give us the value of X and Y that solves this linear system. So these are just the variables that we use, X and Y. And then B is our result or answer matrix, right? This is, you can see that it's a column matrix with just the constant values that each of these equations equals. Notice that if we multiply matrix A times matrix X, we get our equation, 2x minus 3y and x plus 5y. And so to model these linear system, we could say that the original system is equivalent to the single matrix equation AX, because remember when we multiply matrix A times matrix X, we get the expressions on the left side, and this has to equal matrix B on the right. And so we can see that these are equivalent to the original system of linear equations. Now, we're going to take this kind of knowledge and manipulate it. You don't need to know this proof, if you will, or algebraic manipulation. But we're going to show you, I want to walk through the steps of why this works. All right. So first we're going to multiply both sides of the equation by the inverse of matrix A. Okay. As long as we're doing something to both sides of the equation, we should be fine. And then on the left side, what we're doing is we're using the distributive power, the associative power, and multiplying the inverse of matrix A times A and grouping those together. Well, remember that if you multiply a matrix by its inverse matrix, its multiplicative inverse, you get the identity matrix. Do you remember what an identity matrix is? It's that square matrix with ones on the downward diagonal and zeros everywhere else. Okay? So we get that the identity matrix times the variables is equal to the inverse matrix times the inverse of matrix A, which is the coefficient matrix, times the answer matrix. Well, remember that the identity matrix times any matrix is simply that matrix, so we can drop the I from the left. And so if we want to find the value of variables in a linear system, we can simply take the inverse of the coefficient matrix, the constants on the left, times the answer matrix, or the constants on the right. And this is the formula that you really need to know, okay? This is the inverse matrix way of solving linear systems, okay? Suppose that a system of equations with the same number of equations as variables is written in the matrix form as AX equals B. We just saw this in the last example, where A is the square matrix of coefficients, X is the column matrix of variables, and B is the column matrix of constants or answers. If A has an inverse, then the unique solution of the system is X equals the inverse of A times B. Okay? Notice this only works if A is a square matrix of coefficients. B is again the answer matrix, if you will, but the important thing here is for you to remember this formula. The inverse of the coefficient matrix times the constants or answers equals the variable values or solutions. So let's try this. I want you to get your calculator out and see if you can set these up. First, let's set up the coefficient matrix. Our coefficient matrix is all the values on the left side, and we can see it's a 3 by 3. Okay? So first we need to create matrix A, right? Which would be 1, 1, 1, 2, 3, 0, 1, 2, 1. And again, it's a 3 by 3, or the order of the matrix is 3 by 3. Okay, so there's our coefficient matrix. The next thing we're going to do is create our column matrix for the answer. This is a 3 by 1 because there are 3 rows and 1 column. Okay. Next, we're going to try to go ahead and solve this using the formula. So to do this, we need to select matrix A. Just get out of the matrix button, select matrix A, and then hit the X to the -1 key. This is the same as the matrix key. And then select matrix B so that you're doing a product. And then hit enter. And this is what you should get for the value of the variable. So X equals 7, Y equals -3, and Z equals -2. So this is a different way of solving the equations. We could have built this as an augmented matrix as we've seen in prior chapters and sections. However, we need to know how to use this formula to solve special problems that we're going to look at, specifically economic problems that we're going to look at in this section. So see if you can do this other simple problem. Again, create matrix A, which is the coefficients, create matrix B, which is the answers, and then use the inverse of A times B to find the solution. If you notice, as soon as you try to get to the inverse of A, you'll see that the inverse of A does not exist. What this means is that there is no solution to this linear system. Okay, so I just wanted to show you that quick possibility, but hopefully you tried this. At least go ahead and try to put in matrix A, which is 1, 1.5, 2, 3, a 2 by 2 matrix, and then do the A -1 button, just so that you see what the error message is on your calculator. Okay, let's try another one here. Again, here our matrix A is going to be a 3 by 3, and our members are going to be 1, 2, 3, 2, 3, 2, -1, -2, -4. We're then going to create matrix B, which will be a 3 by 1 matrix with elements 10, 6, -1. When we plug this in, A, X -1 key, times B, we should get this answer matrix here, okay? If you need to figure out how to do those steps again, go back to the prior example. So an interesting application of matrix theory to economics was developed by a really incredible guy, a Nobel Prize winner, Wassily Leontief. His application of matrices to the interdependencies in an economy is called an input-output analysis. In practice, input-output analysis is very complicated with many variables. In this situation, just to get you kind of familiar with the concept and the theory, we're going to use simple examples with just a few variables. Input-output models are concerned with the production and flow of goods and services. A typical economy is composed of a number of different sectors, such as manufacturing, energy, transportation, agriculture, etc. And each sector requires input from the other. For example, let's just take a simple concept. Like let's say you're producing food, you're producing corn to be used by the economy. Well, in order to produce that corn, you're going to need maybe gas to run your tractor. So that's from another sector of energy sector. Once you've got the corn, you're going to have to transport that to the market. So you need something from the transportation sector, etc. Maybe to make gas, you use corn or ethylene. And so you use some corn or agriculture to make the gas. So you can see that all these are interrelated and they all have inputs and use some of the outputs from other sectors. Okay. Each sector requires input from other sectors and possibly from itself to produce its output. Again, if we use the corn, we're going to have to save some of the seeds from the corn for the following growing season. For instance, manufacturing output requires energy, transportation, and manufactured items such as tools and machinery. If an economy has n sectors, n representing a number of sectors, then the inputs required by the various sectors from each other to produce their outputs can be described by an n by n matrix. So if we have n sectors, what we're going to have is a square matrix of that same number. So our matrix is going to be n by n. So if we have 3 sectors, we're going to have a 3 by 3 input-output matrix. This is also sometimes called the technological matrix. Okay, so let's look at an example. Suppose a simplified economy involves just 3 sectors: agriculture, manufacture, and transportation, all in appropriate units. The production of 1 unit of agriculture requires 1/2 unit of manufacturing as input and 1/4 unit of transportation. The production of 1 unit of manufacturing requires 1/4 unit of agricultural input and 1/4 unit of transportation. The production of 1 unit of transportation requires 1/3 unit of agriculture and 1/4 unit of manufacturing. Write the input-output matrix of this economy. Okay, when we read this, it does seem very complicated, but the input-output matrix is really quite simple to build, and we just need to take our time and pay attention to the details. Okay, since we have 3 different sectors, we're going to have a 3 by 3 matrix. Okay, each row and each column is labeled by a sector of the economy as shown below. The inputs are the titles of the rows. The outputs are the titles of the columns. Okay, so let's go back and see how we did this. 1 unit of agriculture. To have an output of 1 unit of agriculture, we require 1/2 unit of manufacturing and 1/4 unit of transportation. To output 1 unit of manufacturing, we require 1/4 unit of agriculture and 1/4 unit of transportation. Do you see how this is working? The outputs are here, so to output 1 manufacturing, we need 1/4 input of agriculture and 1/4 input of transportation. Similarly, the production of 1 unit of transportation requires 1/3 unit of agriculture and 1/4 unit of manufacturing. Okay, so again, the outputs are across the top, they're the columns, and the inputs are the rows. Okay. So in order to output manufacturing, we need 1/4 of agriculture and 1/4 of transportation. Okay, production is the output. You produce something, you output it. Okay, example 3 is really a bit unrealistic, as that no sector of the economy requires any input from itself. As we mentioned, the simplest kind of conceptual way is when you think about being a farmer, if you're growing corn, you've got to save some seed. You've got to save some of your output as input for the following cycle of growth. Before we move on, go ahead, hit pause, and create the input output as matrix A in your calculator. You should already know how to do this from prior sections. So we've created the input output matrix. But the input output matrix only gives us a partial picture of an economy. We also need to know the amount produced by each sector and the amount of the economy's output that is used up by the sectors themselves in the production process. We've got this in a unit base for the input-output matrix, but how much total corn or how much total agriculture, manufacturing, transportation are produced? That's what this is talking about. Not just in units about creating it, but how do we, how much is actually produced, what's going to be left over, etc. The remainder of the total output is available to satisfy the needs of consumers and others outside the production system. Now, what does that mean? So let's again go back to the concept of the corn. So let's say we produce 1,000 units of corn is our output for a season. But we know that we have to save at least 100 units to be used as seed for the following year. And maybe we know that in producing our transportation, our ethanol, using that corn, that took 300 units, okay, of our output or our production. So already, even though we've produced 1,000 units, we need 400 of those units as input to other sectors. And perhaps we need something in manufacturing as well. So that just leaves a balance of 600 so far units of corn that we can then use in our community or in our system. Maybe that's then what's available for us to eat or to support ourselves. Consider the economy whose input-output matrix A was found in example 3. Suppose this economy produces 60 units of agriculture, 52 units of manufacturing, and 48 units of transportation. Write this information as a column matrix, listing the sectors in the same order as the rows of the input-output matrix. So we should have agriculture as top, manufacturing in the middle, and transportation in the bottom. And you can see that that is exactly what we've copied here. Create this production matrix X in your calculator. These are how many units of output we had from each sector. So far we've created an input-output matrix. We've created a production matrix. Now let's see how we're going to use this. Consider the economy whose input-output matrix A was found in example 3, and suppose this unit economy produces 60, we've already done this, I'm sorry, I'm reading this again, this is from before. Now, how much from each sector is used up in the production process? So in order to make 60 units of agriculture, 52 of manufacturing, and 48 units of transportation, how much do I use in creating these outputs as inputs to the other sectors? This is what we were just talking about with the corn example. The matrix AX gives the amount of each sector that is used up in the process. You've already put these in your calculator, so go ahead and do matrix A times matrix X. And this tells us that we have, we've already used, of the 60 units of agriculture produced, we have to use 29 of them for this system. Of the 52 units of manufacturing, we've used 42 units. We only have 10 left. And of the transportation, of the 48 units we produced in transportation, we've used 28 of those, meaning we only have 20 left. Okay. Find the matrix D equals X minus AX and explain what its entries mean. So we've got X. You can put this all in as X minus AX. It might not be a bad idea for you to do that. Or you can simply do, the subtraction for these two matrices that we found in the same problem previously. Okay, so our matrix D gives us when we do the subtraction of matrix X minus the product of matrix A times matrix X, we get a column matrix of 31 units, 10 units, and 20 units. 31 agriculture, 10 manufacture, and 20 transportation. Okay? This matrix D lists the amount of each matrix that is not used up in producing in the production process, and hence is available to groups outside the production process, such as consumers. This is the extra. This is what we have to take care of ourselves, maybe to feed ourselves, to drive ourselves to things outside of the production process, to build other things, etc., in the manufacturing process. For example, again, 60 units of agriculture were produced, but 29 units were used up in the process of producing them. We had to use so much corn or ethanol for the gas for the tractor, etc. So while we did produce 60, we used 29 of those in that production. So 31 is the amount of agriculture that is available to be used out elsewhere. This is called the demand matrix. This is called the demand matrix. All right. So let's kind of do a quick review. We started with the input-output matrix. For a system with n sectors, this is an n by n square matrix. Okay, remember that the output is across the top and the input is across the side. Input is the rows, output is the columns. We then created a production matrix looking at what we would output, how much output from each sector is coming forth. This is a column matrix, okay, with the same number of n rows as there are sectors. And then we figured out a used matrix by multiplying the input-output matrix times the production matrix to figure out how much of each sector was used in the production process. And finally, we figured out the demand matrix, what we would have left over to use in other areas of our society or system. And this was found by X, matrix X, the production matrix, minus the production matrix times the input-output matrix. Okay. In example 4, we knew the input-output matrix and the production matrix X and used them to find the demand. In practice, however, this process is reversed. And can you figure out why it would be reversed? I mean, conceptually, why would we need to know the demand before we would know the production? Well, let's go back to that corn example again. And I'm using corn as simple, but let's use all agriculture, etc. If I have a population in my system, let's say this system is only taking care of one community, and I have a population of 100 people, and I need to feed those people. Well, how much agriculture do I need to produce to feed these people? Well, first of all, I need to know how much we need, how much food we're going to need to survive, right? How much agriculture am I demanding? So we start with the needs first. So if I have a population of 100 people, maybe I need 1,000 units of agriculture to allow all of those individuals and community members to survive. Well, if I need 1,000 units and I have an input-output matrix, then I can figure out how many units do I have to produce in order to have that 1,000 left over. And so that's why the demand is always figured out first. How much do we need? And then based on how much we need, we figure out how much we have to produce, knowing that some of that is not going to get to us because it's going to be used up in the production process. In most systems, we know what we need, demand, and use this method of calculation to figure out how much to produce to meet demand, recognizing some of the output from the production is used in production. Okay. So again, looking at what we did in the very simple first example, remember that when we have the demand equals the production minus the production of the product of matrix AX, the input-output matrix times the production matrix, and then going through that same kind of proof, the identity matrix times x minus ax. Remember, the identity matrix times the matrix is the same value. Okay. I can then use the distributive property to factor out an x, I minus a times x. And then this is kind of weird, but it actually works. If I divide both sides of the equation, I minus a, then I get I minus a raised to the power of -1 times d. And this -1 actually works as the inverse matrix as well. So it's a nice formula, okay? You need to know that how to find the production matrix. How much do we need to produce matrix X given an input-output matrix and a specific level of demand, or a demand matrix? This is a very important formula for you to know. Now be careful. This formula, if you remember from matrix multiplication, A times B does not always equal B times A when we're talking about matrix multiplication. So you must do this in the right order. The identity matrix minus the input-output matrix, inside parentheses, take the inverse, x to the -1 button, times the demand matrix will give you the answer. Do not do this in the wrong order. Okay, so let's look at this. Suppose in the 3-sector economies of examples 3 and 4, there's a demand for 516 units of agriculture, 258 units of manufacturing, and 129 units of transportation. What should production be for each sector? We already have the input-output matrix A, so we just need the identity and demand matrix. Here's our input-output matrix. We've already had this one since the very beginning. Remember, our identity matrix will be the same size, but it will be 1s in the downward diagonal. The identity matrix is the same size, but it will be 1s in the downward diagonal and 0s everywhere else. We know the demand matrix because that's what's given to us in the problem. So we need to enter all 3 of these in our calculator, A, I, and D. All right? Once we have them, now we can figure out what we need to produce, or matrix X, by using this formula at the top of the page. And you should get that we need to produce 924 units of agriculture, 864 units of manufacturing, and 576 units of transportation in order to have this left over to meet demands of our society. Okay, so you might want to go back and review this again, or review the examples. This formula is very important. I need you to follow through on this and learn about each of these matrices and be able to solve these input and output analysis problems.